It's not true. Vacuum tubes are very much there. But the way the tiny semiconductor crystals that brought the revolution, that has completely changed. So if you look at electronics engineering, you have specifically two areas where we can say that electronics has made an impact. One is your so-called electrical communication. Uh, that has completely changed our concept of communication, how to communicate. And another field is the electronic devices and the electronic circuits, which are known as integrated circuits. And these electronic integrated circuits are used in almost all systems, which are electronic systems. So these are the areas, and whatever development in any area of electronics you can imagine has been possible because of the tremendous growth in the field of semiconductor devices and technology. That is the basis and responsible for all kinds of development in all areas of electronics engineering. Vacuum tubes, the basic problem was, as you know, that the vacuum tube used to have a cathode and an anode. And when you hit the cathode, electrons were emitted and they are collected by the anode. And by putting some grid structure, we modify this and you can get properties like amplification. A simple vacuum diode can rectify a signal, just like a diode you understand today. And then by putting some grid structure, etc., you can have a control on the movement of the electrons and you can achieve amplification as well. So these devices used to be very bulky and they had application mostly in military situations, in your radars and other military equipment they were used, and in other appliances like your hearing aids. These valves were used in the beginning. Those who are short of hearing, there used to be an amplifier which used to amplify, and these vacuum tubes were used largely for amplifying those signals. So that was the major use both in your civic situation as well as military situation. This electronic component was used to be used for, and these vacuum tubes almost ruled this electronic industry for half a century nearly, almost for 50 years. What I've shown in the previous slide is that how this size went down of this, but still if you compare it with an electronic device, which is a semiconductor device, this size is much larger and heavier than those semiconductor device components, right? So there's an interesting story. I said that mostly it will be a kind of storytelling because it's very interesting to see that even though Fleming invented this thermionic bulb, but he could not get the patent right for his invention. And if in electronics, I believe in all areas, on all fields you'll find. And why I'm telling you the story is see that how important is this. Today, you may be hearing that all of us talk about patenting your invention, file a patent for whatever invention you have, because there are lot of commercial value in your invention. So in US and almost in all Western countries, you'll find that whenever there is an invention, people used to rush to patent office for filing a patent for the invention. And for all major invention, you'll find that there are several people who have claimed that they have invented it. Telephone is an example. Even though Graham Bell is recognized for invention of telephone, but this Bell Telephone Lab, they had to fight several litigation, many people claiming that they were the first inventor of telephone. Similarly, every invention you'll find that a lot of people had simultaneously a similar idea and they immediately rushed to patent office for filing the patent because they used to see a lot of money, commerce involved in this invention, which in India probably we used to neglect that. And one of the biggest example is J.C. Bose, who was very reliant in filing patent. And rest of the story you know. Even though in this area, he had the patent in the year of 1904 for his research in the detection of your microwave radio signals. So he used to have these detectors, and he patented it in 1904. But his other invention was not interested in patenting or in the commercialization of his invention. He used to believe that knowledge is for sake of knowledge only, it's not for earning money. Anyway, but now why now recently we have realized that why this patenting is important and why your information of the intellectual property right, you should reserve that right. Uh, so this story, if you see that 1904 he filed the patent, but Supreme Court invalidated his US patent application on the ground that this thermionic emission, this phenomenon was known beforehand. So he has not done anything new. So his patent application was rejected in the US Supreme Court. So Fleming remained acknowledged for his invention without having a patent right. But that time people didn't realize the power of his invention. And this device played a crucial role in the Second World War for the Britain. Right, because these devices were used in radar signals and detecting RF signals. But interestingly, Fleming lived a long life and he could see the power of his invention, even though he didn't get the patent right. But he got other awards in 1929, and he was honored by Institution of Radio Engineers also in 1933. Then vacuum tubes continued to rule this electronics industry for next 15 years. Up to 1950, around so 1904 to 1950, vacuum tubes were dominating this electronics market. But soon they got replaced by more sophisticated and tiny solid-state devices in the mid of 20th century. But as I've already mentioned that microwave tubes are still very much in use in certain limited areas where you require very high power. And semiconductor devices, because of their limited size, they cannot dissipate a huge amount of power. And for high power applications, these semiconductor devices are not preferred. Vacuum tubes are used. One example today you can see in broadcasting, when you go to transmission stations, you'll find huge size vacuum tubes are there to generate power at a very high level. And in microwaves, you know that there are a lot of applications of these microwave tubes. Now, invention of transistor. This is every invention here in the field of your semiconductor device. All of them a nice story, and it is no less than a filmy story. It will look like that so many people thinking on the same thing and claiming that he is the inventor. There are a lot of examples. So I'll touch upon the major breakthrough work and which has helped this semiconductor industry, manufacturing industry, to grow in leaps and bounds. So Second World War effort produced extremely pure germanium crystal. If you go to the history of semiconductors, you'll find that the history of semiconductor is actually older than the history of electronics, so-called electronics engineering. Because many researchers used to use these compound semiconductors, which used to come in the form of some ore, like your lead sulfide or some other materials, and they did some studies. The studies are very scattered, not all very application oriented, but they studied certain properties of this material. So that way, if you say that semiconductor history, you can say it is older than the so-called electronics engineering, which was born in early 20th century. So Then point contact mixer, they were used in radar using this germanium crystal. And the first solid state diode, which just a solid state counterpart of the vacuum tube, which was invented by Fleming, that was done Bell Lab. And Bell Lab has contributed a lot in the field of devices. You will see that almost every devices, Bell Lab was associated some way or the other. And the germanium crystal was produced in Purdue University, USA. World War II, you must have heard the name of William Shockley. William Shockley is a person that was contributed immensely in the field of your semiconductor devices, right? And you know that he invented transistor as William Shockley proposed that he wanted to build a triode valve. Triode valve is the vacuum tube, and which can amplify a signal. So Shockley thought that it will be possible someday to make a solid state version of this vacuum tube, right? Solid state we call semiconductor devices are solid state devices in the sense that whatever areas are there, if you compare it with vacuum tubes, the electron actually leave the cathode and they are collected by the anode and they travel this vacuum space. But here, all these carriers flow through the material, they never leave the material. So they travel through the material. So all semiconductor devices are sometimes referred to as solid state devices also. And William Shockley secured some funding and lab space and went to work with two other young scientists. One is your Bardeen and the other one is Bratton. So got some space in Bell Lab and started working on this transistor. So transistor invention was not an accident. It was a consolidated approach for making a transistor that a solid state version of triode has to be there, and that was the idea of Shockley. And Bardeen and Bratton, they were both working under Shockley in the Bell Labs. Now, during this working on this transistor, one day Shockley was absent, and Bardeen and Bratton made one experiment, and they were successful in making a transistor. So they made a point contact transistor on germanium. And when Shockley came back, they demonstrated it, and Shockley was furious. He said that in his absence, and he was guiding them, and in his absence, they made this transistor. And Shockley, since he was not present, he didn't get any credit for this transistor, point contact transistor. Then Shockley was very much annoyed with both Bardeen and Bratton, and then he decided that he will have his own way of making a transistor, which we later called junction transistor, because this transistor was point contact transistor was very different. As you know that there used to be a kind of semiconductor devices in the early days, which you used to call a point contact diode, cat whisker, where you have a semiconductor material and you place a metal wire across the semiconductor, and that acts as a diode. So Shockley, a different kind of transistor, which we understand as transistor, bipolar junction transistor, he invented. So he stayed that time in a hotel and worked in a very systematic manner. And finally, he just few months after that, he succeeded in making a junction transistor. And there is a very interesting paper. Those who are interested can read that paper, which was published in 1976 in IEEE Transaction on Electron Devices, where Shockley has given the details that how he developed this junction transistor. And there are photocopies from the diary of your Shockley, where every day used to go into lab and try to make this junction transistor. He failed number lines. Finally, he succeeded in making the junction transistor. Now, immediately after that, Bardeen and Bratton, they filed a patent, and the patent was granted in 1950. So 47, they invented the point contact transistor, and 50, they were given the patent right. Then Shockley filed a patent for his junction transistor in 51, right? And this invention of transistor is a turning point for the semiconductor industries, because so long you could just detect a signal, radio signal, or you could convert an AC signal into a DC signal by using the diode, which either a vacuum tube diode or semiconductor version of the diode. But amplification and switching property was not possible. And invention of this transistor made it possible to have the function of both switching as well as amplification. So that way it is a turning point. Now you can not only rectify a signal, AC signal to a DC signal, but at the same time you can amplify AC signal. So this is a replica of this junction point contact transistor, which was developed by Shockley, Bardeen and Bratton. Right, but this initial this thing was actually developed by Bratton, and Shockley, as I've already told, that Shockley was not there. So this is a photo image of the three people working in the lab, and they got the Nobel Prize jointly. Shockley shared Nobel Prize with Bardeen and Bratton in 1956 for their invention of transistor. But many people that they worked in a group and the transistor, for that they got the Nobel Prize. But the story is a little different. Shockley's transistor was little different from what Bardeen and Bratton proposed. Right. Now, once the transistor was developed in Bell Lab, as I told you that Shockley initially worked in Bell Lab with Bardeen and Bratton to make the transistor. And Bell Lab was very hopeful that this will be the market and they will earn a lot of revenue out of that. But initially, it didn't go well, right? So they publicized it in press, in scientific journals also, but didn't hit the market immediately. And in 1956, Bardeen, Bratton, and Shockley, they got Nobel Prize. And late 50s, Bell Laboratory licensed it freely, just to make it more popular, and so that people are interested to make these transistors. Now, there was some confusion that whether one will continue with germanium or silicon. You know that these two materials, germanium and silicon, these are elemental semiconductors, right? And I don't know what kind of, I think it is a mixed audience, and I presume that they have a basic knowledge of the semiconductors. But in the general interest of people who are not directly related to this area, I'll tell them that semiconductor is a material which has conductivity in between insulator and conductors. The beauty of semiconductor material is that its conductivity can be controlled in multiple ways by adding impurity to it, changing the temperature. So a lot of ways you can make a device shining light on this material. So a lot of ways you can control the conductivity, and that gives you a flexibility of making devices out of this. Otherwise, electrical engineering, larger the conductivity, more preferred will be the material. But since you can have a control over the conductivity, it gives you the flexibility of design a lot of devices. And that's why the semiconductor materials are very, very important. And if you see the periodic table, you'll find two elements are there which satisfy these properties of the semiconductor. One is germanium and another is silicon. They belong to group 4 of the periodic table. Apart from this, you have a host of compound semiconductors where you can make a combination of materials, elements from group 3 and group 5, group 2 and group 6, group 4 and group 4. So you can make a lot of other semiconductors. Many of you must have heard about gallium arsenide, indium phosphide, indium arsenide, aluminum arsenide. These are all examples of binary 3-5 semiconductors. Likewise, you have cadmium telluride, Bankari cadmium telluride. These are 2,6 materials. So you have elemental semiconductors as well as compound semiconductors, right? Just I mentioned in the interest of those who are not really in this field. Now we see that whenever there is an invention, there is, you see, some people can see there is some commerce and there's some money in that invention, and all the fights start from there, right? And William Shockley, then when this invention was there, and Shockley was not liked by his co-workers because of had a different kind of attitude, and many of his co-workers didn't like him actually. And Shockley soon was not in good book of Bell Lab. Then Shockley decided that since the transistor is now going to pick up, so why not to open a new company? And he left Bell Lab. And that time his mother was also ailing, so he came back to California, right? And set up his own lab. And that is Silicon Valley as you know it today. So 2 more young engineers he brought along with. He tried to lure many of the people who were working in Bell Labs, and he started his own company. But again, this company also many people left because, as I said, I told you that in invention there is a lot of money involved in it. Sorry, I guess I missed one. Okay, so let me tell about this story. That Shockley developed a lab. That Shockley
Sir, you are muted, sir. Sir, please unmute yourself. Sir, please unmute yourself. Sir, please unmute.
Sir, muted.
Sir, unmute, sir.
Sir, you are muted, sir. We can't hear, sir.
Sir, unmute yourself, sir. Sir, unmute yourself, sir. Yeah,
Can't hear, sir.
Can you hear me now?
yeah. Yes, sir.
Yes, sir.
So you can see my presentation? Can you see my presentation?
Yes, sir. We can see, but you are muted.
Yes, sir. Okay, now.
It's okay now, sir. It's okay now.
You can see now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So Shockley started his new company with some of his colleagues who were working in Bell Lab. But after some time, 2 young engineers with another 6 people whom actually Shockley hired for semiconductor laboratory. They left Shockley because again I said that because of Shockley's attitude probably. They left and they started a new company, which is Fairchild Company. And they was quite annoyed with these people and they called these 8 people as, treated as 8 people. They were disloyal to Shockley because Shockley used to make certain decisions without caring for others. One point of time he said that he'll not work with silicon. And people working with him, they were very unhappy and they left and started a new company. And Shockley somehow then brought a new culture by hiring the young graduates of universities. And this is a culture which is still now existing in Silicon Valley. And in North California region, you have a lot of companies, right? And most of the companies initially used to be your silicon because silicon manufacturing industries were growing that time. So in Silicon Valley, most of these companies were this. Nowadays, you'll find a lot of IT companies are there. So instead of banking on people who are experienced, Shockley thought that it is better to get the young graduates from university and use them for his lab. And this culture is still continuing in Silicon Valley. And people say that silicon, actually in Silicon Valley, silicon was brought by Shockley. So, and now you find a lot of the giant companies of IC manufacturing companies are there in Silicon Valley, in North California. So soon after that, there was a lot of modification in the basic structure of the transistor. And Fairchild in 1959 introduced the planar technology. And after that, there was another new invention. And this invention is the integrated circuit invention. Right. So long as the devices you make used to be discrete device, a diode or a transistor. Now, 2 scientists were there who almost simultaneously devised this method of making all these devices on one substrate, right? And then interconnecting this. That is the basic concept of integrated circuit. We call monolithic integrated circuit. So one basic substrate is there, and the entire circuit will be laid on this substrate, right? And 2 scientists were involved. One was from Texas Instruments, Kilby was one, and the other one was from Fairchild, Robert Noyce, who was the co-founder of Intel also. So this structure, both the objective was the same, that all the devices will be on one substrate. One substrate means one static material is silicon. Substrate if you take, all devices will be made on this. They will be interconnected. In the Kilby structure, which he proposed, he used a block of material. He worked with germanium crystal and make these blocks, different transistors, and then he interconnected them with the help of wires, and no discrete component was used in his device. And early days it was not called ICs. Later on this terminology came. When they filed their patent, the patents were in different names, not in the name of integrated circuit. So Texas Instrument and Fairchild, they are also competitors, right? Now Robert Noyce, he said that he made a similar kind of structure on one substrate. He made a lot of devices grown on that, but instead of using connecting wire, he used evaporated aluminium to interconnect those devices. So that is the true form of integrated circuit, what we understand today, right? You connect these basic blocks with the help of conducting parts, which are evaporated metals, right, which connect. But the objective was that on one your substrate, the entire circuit will be developed. Is the essence of integrated circuit. Now that story started. Now this is one of the turning points in the semiconductor industry. From discrete devices, you can make many such devices and you can realize an electronic circuit in one block. So this is a major breakthrough and turning point. And after integrated circuits came in, there is a tremendous development in semiconductor manufacturing industries, right? And lot of components in the early stage. They made flip flops. Then using these flip flops, the basic logic circuits, they developed many other circuits. Then later on, calculator was also made using this integrated circuit. So these are all stories in the early 70s. This development were there. But today, if you see, the technology has come a long way, and I'll talk about that. But before that, let us see. There's an interesting story that how the fight in between your Fairchild company and Texas Instruments, right? Because this is a new technology which is going to come, and again there is a lot of money involved in the invention. So in the year 1958-59, the Texas Instrument, Kilby and Robert Noisy, they almost simultaneously they developed this concept of integrated circuit. And Kilby was awarded, was given Nobel Prize in 2000 for his invention. And Noisy was a co-founder of Intel. He also filed patent, and the patent was in the name of semiconductor device and lead structure, not an integrated circuit. And similarly, Kilby, when he filed his patent, it was called miniaturized electronic circuit, right? Now, both the companies, Fairchild as well as your Texas Instrument, they started making integrated circuit. This concept they used and they commercialized it. Now there are long legal battle that who is the real inventor of this integrated circuits. Right, in the scientific community, they believe that both are actually responsible for this whatever development in the integrated circuit has happened. Is because of Robert Noisy as well as Kilby. That so scientific community, but again industry, you know that will get the money royalty for this. So they had a long legal battle. After that, the company management they sat together and they decided that both of them will be allowed to make integrated circuit based on this concept. But if any third party wants to use it, they will have to pay right to both the companies. So with this settlement, other companies started also using. Fairchild is a company which has given birth to a lot of big companies afterwards, including AMD, Intel, as your National Instruments. So these are all that came from Fairchild. So these are some of the photo images of the early days of the transistor planar technology, which we are showing. This is the integrated circuit, which was done by Robert Noisy then in late 50s. And this is a simple flip-flop in the integrated circuit form. This is another photo image of a planar transistor where you see that base, emitter, and collector, they are on the same plane, right? Unlike a vertical structure. So in 1962 to 64, then diode logics and resistor transistor logic was developed in this integrated circuit concept. Then you have the TTL integrated circuit, which were a number of companies were there. Fairchild, Motorola, Philips, Sylvania, all these companies, they started. So whenever a third party made this, they had to pay both the companies. Fairchild as well as Texas Instruments. So first commercial operational amplifier came in 1965, that Fairchild 702, and the early operational amplifier used to look like this. So this is the development of integrated circuit. 47 you have seen transistor, 59 bipolar transistor was developed, T8 that working model of your field effect transistor, and 65 first operational amplifier, then 71 came your 4-bit microprocessor. Before that, you had these calculators. Earlier, the calculator used to be of those were electromechanical calculators, they're huge size. Using this integrated circuit, the size was reduced down significantly. And Kilby, we actually first developed these calculators, electronic calculators, as you know today. And in 1971, this electronic calculator commercialized. They are available in the market. So 4-bit microprocessor was in 71, 72, 8-bit microprocessor, and IBM PC was launched in 1981. Right. After this is the story. Now there is another interesting turning point in the semiconductor manufacturing industry, which came with the introduction of MOSFET, metal oxide semiconductor field effect transistors. Right. And today's all these are mostly based on those which are used in for CPU, etc. They are based on this MOS technology. Right. Here, I'd like to mention one thing that conceptually, the field effect transistor concept came long before bipolar transistor was actually proposed and implemented. But there are initially some difficulty. So a practical field effect transistor, this proposal was 30 years, almost 30 years before bipolar junction transistor, which was invented in 47, 48. So much before that, field effect transistor was conceptually known. But the fabrication, there were a lot of difficulties. But demonstration of a successful MOSFET was possible in 1959-60, again in Bell Labs. The MOSFET was developed by Atala and Bell Labs. And in 1962, RCA fabricated multi-purpose logic block comprising 16 MOSFETs on a single chip. You see that the first integrated circuit was made with a bipolar junction transistor. But today we do not use bipolar junction transistor for making CPU chips, right? Because MOSFET has a lot of other advantages, particularly the packaging density of MOSFET is so high that MOSFET eventually replaced this bipolar transistor for high level of integration. But these MOSFETs are very sensitive to static charge, supply voltage, oxide effects. There are a lot of difficulties, but with the maturity of technology, of silicon technology, MOS technology, it was possible to have reliable integrated circuit based on MOSFET. Now in mid-65, C.T. Shah, he proposed a CMOS structure. Initially it started with an NMOS, then a PMOS, and finally a complementary MOS structure using an NMOS and PMOS was developed, and that is the basic core of this IC. So those who are interested in this MOSFET operation, as you know, that MOSFET is a different kind of transistor where the gate is insulated from the channel, right? So bipolar junction transistor uses both the transport of electrons as well as hole, but in field effect transistor, the magnetic carriers only flow. Right, either the electrons contribute to the current or the holes contribute to the current. And this is a structure where you have p-type semiconductor substrate and you have two regions, N plus, on the two sides, one acting as source and other acting as drain. And in between you have an insulator layer. And this kind of devices are generally known as insulated gate field effect transistor, IGFET. So where the gate is insulated from the channel with the help of an insulator. Silicon has an advantage that a natural insulator can be formed on silicon by simply oxidizing the silicon. So it is converted into silicon dioxide and silicon dioxide becomes an insulator. So if you use silicon, then you can design this insulated gate field effect transistor in a very easy way. And that's why silicon becomes so popular in making MOSFET. So metal oxide, we say oxide is silicon dioxide, we mean actually. But MOSFET is actually a member of a bigger family, which is known as insulated gate field effect transistor, or MISFET, metal insulated MISFET, metal insulated semiconductor field effect transistor. Right. So you have one source end, another drain end, and if you consider this structure on a p-type substrate, you will find that two diodes are connected back to back. One is NP, another is PN. So under normal condition, no current can flow through this structure. Right. Now on the top you have an insulator, and you have gate on the top. Right. Now if we apply a positive voltage on the gate, you will find that some negative charges will accumulate at the interface of the oxide and the semiconductor, right, which are shown as the channel region. And if you apply a sufficiently large positive voltage, you'll find that large number of electrons will come, and at the will accumulate near the insulator and semiconductor interface and connect the two N plus region. Right. Then you find that earlier, in the absence of the positive voltage, two diodes were connected back to back, so no conduction was possible. But now the source and drain are connected by a thin layer of electrons. Now, you may ask that where from these electrons come? Electrons are minority carrier in the p-type substrate. They are dragged by the high positive voltage, and they establish a channel. Now, by controlling this gate voltage, you can change this conductivity of the channel, and you can get you can increase the flow of current from the source to drain by this gate voltage. Right. So using this, you can use it as a switch, you can use it as an amplifier, right? Now, the way we have developed NMOS using a p-type substrate, exactly in a similar way, we can use an n-type substrate and make a p-type MOS, right? Earlier MOS was n-type, where conducting path was electron here. Now, instead of having separate p-type and n-type substrate, we use one substrate, and we create an n-type region, which can be done always by counter doping. And if you create an n well, then exactly in a similar way, then this region, that blue region, this region actually becomes an n-type material, where you can develop another PMOS structure, almost similar to this, but the voltage required in the gate will be just reverse, negative. And so on one substrate, you get these two devices, NMOS and PMOS. And once you connect this in the fashion which is shown in the circuit symbol, you get a Cmos inverter. And this is the heart of your today's semiconductor ICs. All these logic gates and other things you can develop with this basic inverter structure. And a NAND gate has been shown using CMOS logic, how you can realize a NAND gate. All gates you can realize with the help of this CMOS. So CMOS inverter is the heart of all these ICs. So this is the photo image of IC in 1967, MOS-based IC. And this was Intel 404 microprocessor, which was in 71. And 8008 in 72. That's the photo image of this. Now, the whole purpose of this integration is the objective was to bring as many devices as possible in one block of semiconductor, right? And then interconnect them to have different functions as different circuits, right? So that is the whole purpose of this integration. And initially, the integration was on a very small scale level, and it was only a few transistors, some tens of transistors. Initially, when this IC was fabricated, then it was in that level. In 60s, it became on the order of hundreds of transistors in each chip. One chip size is typically a postal stamp size. And now our objective is that how many devices we can put into this stamp size your IC and integrate them, right? And how this has evolution has taken place here, that there's a dramatic change in the number of individual devices which you can put into one die, one integrated circuit block, right? So when it was hundreds of transistors, it was medium scale integration, and mid 70s we started your large scale integration, where tens of thousands of transistors were put, right, which were used initially in calculated chips and the first microprocessor. Now, true LSI circuit approaching 10,000 transistors began to be produced in 1974. The computer main memories and the second generation microprocessor. The final step was started in 1980s and still it is continuing, is very large scale integration. The development started with hundreds of thousands of transistors in 80s and continues beyond several billions transistors as on date. So billions of transistors you can in one integrated circuit, right? And today we call it ULSI, ultra large scale integration, where we are thinking of putting trillions of transistors in one IC. How is it possible that we can put so many devices in the same size, postal stamp size IC? The thing is that we are reducing the size of the individual devices, right? So, and this scaling is possible in the case of MOSFET transistors, MOSFETs. So MOSFETs are used, and using the scaling property of this MOSFET, we can put more number of MOSFET transistors in one IC and achieve this, ultimately having trillions of transistors in one IC. But there are certain restrictions in achieving this. One comes from the technological limitation, the other will come from the physical limitation. As we will see, there's a physical limit, how small a device can be. You cannot go to the atomic dimension and have the size of the device. And what you normally understand by the size of the device, as you have seen, basic MOSFET structure, you have the source and drain, and you have a gate in between. Now the electron has to travel, so for example, from source to drain. So how much time does it take from traveling from source to drain? So it will depend on the distance between source to drain, which is in a self-aligned structure is almost equal to the gate length. So one way we say that the device size is equivalent to gate length. And if the gate length is L, then L divided by the velocity of the charge carriers will be the time taken by the electron to reach the drain. Right. Now we are trying to reduce this size. If you reduce this, then the time taken by the carrier to travel from source to drain, because unless it reaches the drain, it cannot flow through the external circuit. Right. So this time is reduced, the device will be faster. So we call this time as transit time. The time taken from source to drain is transit time. So 1 upon twice pi of this time is the maximum frequency the device can handle. Right. The frequency would be decided by this. Now scaling, when we do scaling, we are reducing the size of the individual devices and trying to put more and more devices. Now Gordon Moore, who is the co-founder of Intel, he gave an empirical law, and later on you'll see that industry has followed almost his prediction of miniaturization. So how much you can reduce the size and how much time it will take. He related this the number of transistors which you can put in one die of this IC, one IC block, and how much time it will take to achieve that goal. So he predicted that. So the approach is to make smaller devices and to shrink the dimension of all the circuit components by a constant factor. So if you reduce the gate length, all other related parameters, quantities will be affected, and that process is called scaling. So scaling proceeded at the exponential rate, and Gordon Moore predicted that doubling the number of transistors on a chip approximately every 18 months. So every 1.5 years, it will be possible to double population of the devices in a particular chip. The number will be doubled. And this law is known as Moore's law. So the first microprocessor had only 2200 transistors. We are looking at something a million times that flex in next generation, a billion transistors. And what that gives us in the way of flexibility to design product is phenomenal. So this was a statement of Gordon Moore, and his prediction was this. And if you see that with years 1960 onwards, we have these different CPUs which were developed, and the way it has grown, that per die how many transistors there. So this is depicted here, and it has almost the prediction is shown by this line. Uh, so 1975 the projection was this, and for memory devices the red color we achieved this. And for microprocessor, this triangular one is showing that it started with 404, and then with these titanium processors, and now these new technologies are being used after that. This is a world photograph where it is showing that industry has followed that Moore's prediction that way. When you reduce the size of these devices individually, that is not sufficient for integrated circuit, because we have seen that in the integrated circuit, these individual devices or blocks are to be interconnected by conducting paths, right? So when you reduce the size of this IC, these conducting paths also come very close to each other. And when this happens, then there will be a lot of parasitic effects, right? So reduction of this is not only just reducing the size of the device will not be enough. You'll have to see that how will you maintain this distance between this conducting also. This is in technical terms, this is called node, right? Node refers to the metal pitch used in the product, right? So what is the partition between the metallic interconnects, right? So that is also very, very important. So both the things are shown here, that size of the gate is reduced from say 200 nanometer, 130 nanometer, 70 nanometer, 50 nanometer. We reduce the gate size to 30 nanometer, 20 nanometer, 15 nanometer. Even companies like AMD, Intel, they are claiming that they have reduced this gate length to 7 nanometers. Right. Now, it's not surprising that this gate length has been reduced, but what is surprising is that how these devices continue to work at such a gate length. That we need to see. And if you see on the technological node on the other side, that separation between the conducting path is 30 nanometer as such. So, and since crossover metallic path is also not possible, then there was some idea which was that why not to make this interconnection using optical interconnects. So IBM also worked on that. The processor was developed in which these optical interconnects were used, so that we can increase the number of devices, and this problem we are facing in electrical conducting paths will not be there, because these parasitic effects will not come in optical interconnects. So that was also tried. So Gordon Moore proposed his theory for almost 5 decades back, and the area of silicon chip that remains almost same. Right? This I have already told you. Now, how the whole thing is done? Whole thing is done by using a technology. This IC design is done. How you make so many devices on this? So you take the simple example of MOSFETs. When you see that it has a semiconductor substrate, then on the top of that you have a p-type substrate, you grow n plus region on the two sides. In a schematic it looks very easy, right? But when you go for a real fabrication, you'll have to go through a number of steps for making a single device, right? So how this is done? This is done by a technique which is called photolithography technique, right? So you'll have to make certain metal contacts, you'll have to deposit some insulator in some selected region. So you'll have to use a technology for doing that. And this photolithography technology is something which is very similar to traditional 3D printing. Similar kind of thing is there in lithography we used to do. Lithography is taking photography, repeated photography, and using your some kind of mask which will allow this light to pass through, UV light to pass through and block in certain region. So in certain portion you can cut window and do some processing without affecting the rest of the part. So we generally use photoresist coating. So this photoresist coating are used for your and are exposed to ultraviolet rays, and we develop a mask is a design that in which way you want to say etch out one portion of this. So you prepare the whole design in the form of a mask, and then through this mask you shine UV light. So it is taking like just like camera shot on the substrate, right? And then removing certain portion which can be chemically removed, and then you can do some processing. So repeatedly, if you follow this process of doing this, making use of this photoresist coating, and then removing subsequently, then you can develop just like a camera photo you develop. Similar kind of thing you can do on substrate also and get any kind of design you wish to do. So nearly 50 photolithographic shots will be needed to produce microprocessor chips. So large number of steps you'll have to go through before you get this finished device. Right. Now you may think that, so if you have to do it for all these devices, so then devices must be very expensive. But interestingly, if you see that the cost of a finished IC is not that high. So that way, which is using billions of transistors in one IC, the cost is so low. If you divide it, you'll find the cost of one transistor is less than a paisa. So how it is possible? Because when you produce it in bulk, large quantity, and the same 50 steps will follow, but the production will be in large volume. Right. So these silicon materials, I don't want to get into those technological details, even though I'll show that steps which we follow for doing that. Big size substrates are used for making large number of devices in one go, large number of ICs in one go, and that reduces the cost. And another advantage is that the raw material which is used for making silicon is abundantly available in nature, right? So let us see the miniaturization, as your director was telling that like to know that what is this nanometric sizes and how much we can go down in this. It depends on the kind of this nanotechnology where you are going to use this nanotechnology. For devices, if you say that we can have a few nanometers, right? Tens of nanometers can be grown very easily. But there is a physical limit up to which you can reduce the gate length of a device. Because all these semiconductor devices, they actually, unless it is a quantum well device, they work on the bulk properties of the semiconductor, right? Now this bulk property of the semiconductor will vanish when you reduce the thickness to a level of less than 10 nanometer, right? And the other limitation is the technological limitation. Technological limitation is that photolithography technique you use UV light of certain wavelength, right? And that can give you precision up to a certain level. So you cannot go beyond that. So if you want to go further reduce the size, then you cannot use the traditional photolithography method. Okay, today technology is not there. Tomorrow new technology will come, and probably it will be possible. And as you know that there are other lithography technique like X-ray lithography technique, E-beam lithography technique, which can enable you to achieve gate length which is much shorter than that. Right, but still there is some physical limitation beyond which, sorry, this technological limitation beyond which you cannot precisely design these devices. But the second more important limitation is the physical limitation, even though a lot of companies are claiming that they have done. So this is a general scaling, this property of MOSFET, scaling rules, which is not important for this. But those who are interested, that this is the beauty of this MOSFET device, that by appropriate scaling you can increase the integration. But when you come to zero point 0.1 micron or less than that, you face several problems with your MOSFET devices, CMOS devices. So zero point 0.1 micron means your 100 nanometer, right? So as I already told you that traditional photolithography is not useful. So you use e-beam lithography in this level. Now, industry, there's a semiconductor, the Association for the Semiconductor Industries, which make a roadmap where the industry follow that roadmap. Right. This is not that arbitrary different companies are doing in their own way. They sit together and they decide what will be the roadmap for the future. And unfortunately, India is not there, but there are other countries, European Association is there, Japan is there, Korea, Taiwan is there, then Semiconductor Industry Association is there. They together decide that roadmap for the future. Because I said that there is a dramatic development in the field of this IC technology, IC manufacturing. And the companies, there's a cutthroat competition between all these giant companies who are making the central processing units, like your Intel, then AMD, IBM. So there's a huge competition among all these companies. But they have to follow certain norms. But when you reduce the size of these traditional long channel devices, they face a lot of problem when the size is reduced. So these are the obstacles which comes in your way when you try to miniaturize the device. These are known as Shockley effect, right? If you see the MOSFET structure, I didn't explain that technically how it works here because my focus was a little different in this lecture. There you'll find that a depletion region in the source and drain region, they become considerable as compared to the depletion region which is created just below the gate. It starts affecting this, and then the device doesn't function the way it operates when the channel length is reasonably long. So many short channel effects come there. Then the electric field is high because the dimension is squeezing. So if you apply the 5 volt and then your 100 nanometer, then you can calculate what will be the value of the field. And again, if you reduce the size, that heat dissipation problem will be there. And as I've already mentioned, that you cannot treat it as a bulk device anymore, right? So a lot of problems will be associated when you try to miniaturize this device. So I have shown all of them in this graphic way, that what are the problems you face. That say the dielectric at the gate, which is the oxide layer, right? The tunneling may take place because it is very thin, and now the carriers may penetrate the gate insulator and reach the gate. In MOSFET devices, the gate is insulated, right, and it gives you a very high impedance. But once the leakage is through, then the MOSFET will not work the way it functions, right? And there will be a shallow junction formation. Junction resistance will increase, contact resistance will increase, wear resistance, interconnect, capacitance. All these problems will come in the channel. You will have random dopant distribution, inversion layer capacitance, punch through may take place, right? And there may be direct tunneling from source to drain, and gate will lose all its control over the flow of carriers from source to drain. So this many problems will come when you try to shorten this. Now, one simple calculation we can, that how small we can make the gate length, Let us make a simple calculation. If you look into this operation of these MOSFET devices or field effect transistor in general, I told you it is a majority carrier device, and the carriers flow because of application of electric field between source and drain. So in semiconductors, the two types of carrier flow may take place. One is by diffusion, another one is drift, and there is a third mechanism which is the tunneling mechanism, which is not a cannot be explained by classical mechanics. You take help of quantum mechanics too. So that is another part, another component. But the major two components is one is the drift current, another is diffusion current. So this means that diffusion means whenever there is a concentration gradient, charge carriers will flow from higher concentration to lower concentration. It's just like any diffusion process. You open a bottle of perfume in a corner of the room, and that smell spreads all over the room by process called diffusion. Similarly, in a semiconductor material, if there is a charge gradient, so that it will flow from concentration to the lower concentration unless and until it is uniform. Right. The other one is that if you apply an electric field across a semiconductor, the electrons will flow in the direction opposite to the field, and the holes will move in the direction of the field. And field effect transistor exploit this transport mechanism for making the device. So between source to drain, if you apply an electric field, the carriers will move, right? Depending on whether it is P type, P channel or N channel. Right. What the gate does, gate actually controls the movement of these carriers from source to drain. So it depends on the drift current. And drift current, if you see, depends on a parameter of this material, which is called the mobility of the charge carriers. How fast the carriers can move. Which semiconductors are basically crystalline structures. So when these carriers move through semiconductor, they collide with the lattice atoms, which will be silicon atoms or the impurity atoms. They collide, and they cannot make free electrons that moving in vacuum. Right? It's not that. They get scattered. But since there is an applied electric field, preferably these electrons will move in the direction opposite to the field, holes will move in the direction of the field finally. But that motion is not a straight one, it's a random motion through scattering. So mobility gives that the velocity of the charge carriers per unit electric field. So if you increase the electric field, the velocity will increase. But as you understand that this cannot happen indefinitely. So there is a critical value of electric field after which the velocity saturation will occur. So after that, if you increase the electric field, you'll find that the velocity of the charge carriers will no longer increase. Right. So that is the critical field, electric field, and this is called the saturation velocity of the charge carriers. Now, if we take a typical example, now since it travels through scattering, the whole idea, the operation of this MOSFET devices or any field effect transistor is based on that bulk explanation phenomena that through multiple scattering it goes, reaches the drain finally, and we have the concept of mobility, and based on that we find a relationship between the drain current and the drain to source voltage we apply. Now, if we reduce the gate length to an extent which is even shorter than the mean free path, because the carriers travel a distance between two successive collisions, right? There is an impurity collision or collision with a silicon atom, and there will be a second collision with silicon atom with the carrier. In between whatever path the carrier is traveling, electron or hole, is the mean free path. Right? So between two successive collisions, the path traversed by the carrier is the mean free path. Now, if you try to reduce this gate length below this mean free path, then there will not be a single collision event. And if the collision is not there, will the theory or this mobility theory we have developed based on collision will hold? Then this calculation shows you that The relaxation time is 5 into 10 to the power minus 14 second. If the velocity saturation velocity is 5 into 10 to the power 5 meter per second, which is for silicon, if you use, then the scattering mean free path comes out to be 12 nanometer. This means that if your gate length is less than 12 nanometer, virtually there will be no collision, right? So if there is no collision, how your theory of mobility will work here? If the concept of mobility doesn't work here, how will you calculate the drain current based on that mobility? All these issues will come. But companies are claiming that they have reduced this gate length less than 10 nanometer. So when there is no collision, there's a new kind of transport is there, which is called ballistic transport, right? Without any collision will be there. So a situation when the gate length becomes so short that only very few or there will be almost no collision during the transit from the source to drain. Okay, now previously we discussed lot of problems which are associated with miniaturization, and many of these problems can be overcome by making use of by modifying the structure. And this way, the basic MOSFET structure was modified in different ways. Some people used fully depleted silicon on insulator MOSFET structure. Some people used high K dielectric in place of SiO2. Si3 and 4, that silicon nitride was used, and other high dielectric constant materials were used to get rid of some of this adverse effect of miniaturization. Then silicon and sapphire was tried. So then double gate MOSFET was tried, and then surrounded gate MOSFET and FinFET. FinFET is the new technology which is being used today. Commercially, this kind of transistors are used so we can reduce this gate length and still we can achieve the desired performance. So these are some of the different kinds of gate structure which are made, and in the current MOSFET technology which is used is integrated circuit for making CPU today, CPU. So they are using this kind of structure to get rid of this effect. But we have seen that there is one ultimate limitation after which probably will not be reduced the gate length. Then the question is that is the microelectronics industry is facing a challenge that Moore's law will not be valid? So people have started thinking about beyond Moore's law. Now this formula of every 1.5 years in a particular die you can double the number of transistor will no longer hold, because there is a physical limitation beyond which the device will cease to function, right? But there is a silver lining here that even though this device MOSFET will not work in that way, but it can give rise to many new devices, right, which are called so-called nanoelectronic devices, right? And these devices cannot replace the microelectronic devices which are used for making chips, but they can definitely supplement it. Before coming to that, let us quickly through that how we make these ICs. Very quick graphical representation. It is very interesting to note that the CPU is also made out of sand. Sand is used in for construction of building, is a major component
Sorry,
for the civil
actually,
engineers.
I have some meeting. Okay, excuse me. Okay,
Okay, sir. Okay, sir.
at our institute.
Yeah, I actually I forgot to ask that what is the time given to me.
Okay, sir. It was 1 hour. Anyway, you continue, sir.
No, but 1 hour, then I'll have to go very fast. I'm sorry that I didn't ask about this. But it is interesting that from sand actually you prepare the CPU. No one will believe that from sand you can produce the CPU. Right. So sand is silica is the primary raw material for making silicon. You purify this silica and then convert it into single crystal silicon, cut this single crystal silicon in the form of disc which I have shown here, wafer, and that is your starting material on which you have this lithography using lithographic technique, putting photoresist. You develop this circuit on this block, and this way, and metal conducting path you create. Then you test this device, and on a 12-inch or a 16, 18 substrate, you get so many IC made here. Then you cut those ICs, separate them, test them, package them, and that is what you see as the CPU chip which is used. Right. So now what next? Micro, nano, we are talking of some things, we have so many questions in mind, and if you see that compared with the dust mite, which are of 200 micron size, human hair, 100 micron diameter, DNA has 10 nanometer, these are nature made, and we are claiming that we have made carbon nanotubes of 2 nanometer diameter, right? And other transistors we have already made, quantum dots with 2 nanometer. Right. What I told you that whenever the size is reduced to such an extent, then probably you will not be able to consider the particle nature of these carriers anymore. You will have to consider the wave nature, because quantum mechanics will come into play. And these devices, the traditional microelectronic devices, will cease to work, but will give this part to new generation devices which are called nanoelectronic devices. Examples of these are quantum dot devices, resonant tunneling diodes, and resonant single electron transistor (SET). So these are the examples of nanoelectronic devices. Since time is not there, I will not go into the mechanism of operation of these devices. So this new generation devices has come because of this nanotechnology or nanoelectronics. And but you remember that the goal is not to replace the microelectronic devices. Don't think that this nanotechnology will replace the microelectronic devices of the integrated circuit, but they can be combined with microelectronic devices to make a hybrid kind of IC, and which will supplement the functions of this, but will not. Our objective is not to replace them. So that's the role of nanotechnology here. And carbon nanotubes is that I said that we'll be starting from vacuum tubes and to carbon nanotubes. Recently, carbon nanotubes and graphene, they have been studied. People have studied a lot on this. It is basically an allotrope of carbon with cylindrical nanostructure. And this is the ratio of length to diameter of this. And in electronics, they have applications. And new ICs are being built now with the help of, because you see that the Moore's law is coming to an end, and people are thinking of using this new material on the silicon platform, so that this miniaturization can continue. So MOSFET was built using carbon nanotube, using a similar kind of technology, and it was first demonstrated in 1998. And there was a joint project by IBM and Stanford University. They developed CNT FET based integrated circuit. Integrated circuit. This is the structure, carbon nanotube you see on the other side, and you have a source drain which is connected to with a carbon nanotube, and it's a single channel, and you can have multiple channels, and you can have a device like this. And I'll not go to different types of carbon nanotube based field effect transistor, but talk about the IC. There are a lot of difficulties associated with this, particularly mass production and stability of these devices. IBM at Watson Research Center in New York have become the first scientists to create high density working computer chips from carbon nanotube transistor fashioned using conventional semiconductor processes. Similar processes they have used. Right, with a density of 1 billion transistor per square centimeter and performance in the region of 5 times faster than the silicon transistors. So IBM's breakthrough indicates that carbon nanotubes will be the semiconductor that eventually replaces silicon in computer chips. So now we say that your Moore's law, this traditional microelectronics has come to a crossroad. Now which way this will go now will depend. Will this carbon nanotube based field effect transistor will be the future of microelectronics, or some new technology is going to come? Along with this, MIT researchers also did almost 14,000 CNT they have developed, and they have made a functional CPU chip. And this IBM's chip is 22 nanometer, comparable to 22 nanometer field, right? So they use hafnium oxide on the top of silicon and put these carbon nanotubes, cut a groove on that and place the carbon nanotubes and connect the source and drain. This is the photo image of this. But there's another interesting development that I wrote this history repeats itself because we started with vacuum. Are we coming back to vacuum? Probably there's another concept which is floated where in Cmos technology where the source and drain will be connected through vacuum, right? And electrons will be drawn through the vacuum from source to drain, field emission. And now these devices will be much faster, right? But this will not be purely vacuum, but filled with helium, and the size can be reduced to order of few nanometers, right? And using this kind of concept, this concept which is shown here, NASA's vacuum transistor. So we started our journey with vacuum tubes, and again now all the semiconductor revolution and IC manufacturing developments. Again, we are coming back to get the support from this concept where the carriers can move faster and the device can work. And it was reported that 460 gigahertz up to 460 gigahertz use this conventional silicon field effect transistor. So now what will be the future is very difficult to predict. And all of you must have heard that quantum computers are coming. If quantum computers are coming, probably that will be the end of the your microelectronics because that concept is completely different, and they use superconducting circuits or some other mechanisms for achieving this quantum bits in place of traditional bits which are used in this microprocessor chips. So that technology is different, and it can do computation 3 million times faster than your normal computers. But there are a lot of practical difficulties still associated with quantum computers. And if quantum computers become a reality that way, and if it is used widespread, then probably the end of your so-called microelectronics will be there. But I believe that nanoelectronics per se, that nanoelectronics and nanotechnology is not going to replace your electronic or the IC industries. That is not going to happen. But otherwise, if the whole concept changes, then probably. We never know. And if the quantum computer comes, I'll consider it as a disruptive technology which will take the industry in a completely different direction. Because we predict something for the future, but some innovation comes which takes all of us in a different directions. So that we cannot predict. So journey of electronics started with vacuum tubes of Fleming, and they were soon replaced by semiconductor crystal, and invention of junction transistor was one breakthrough. Then the second was integrated circuit. Then Cmos technology was another breakthrough, and scalability of this MOSFET is one of the features which has made this possible. That trillions of transistors we can put in one chip today. Because of physical limitation of silicon MOS, we cannot further miniaturize these devices. So what is to happen beyond CMOS is to be the future will tell us. Graphene-based FET or CNT-based could be one option, or maybe the vacuum transistor which is proposed by NASA, or this thing will be swept out by the quantum computation that becomes a reality. So that's all. And these are some of the references I consulted. And thank you very much.
Thank you, sir, for such a nice talk. We have more than 90 participants who are listening to you, not only in this webinar but also in our live YouTube. So we have, if with due permission of you, if you allow, sir, can we have a question answer session, sir?
Yeah, yeah,
Thank you, sir.
definitely. Go ahead.
Thank you, sir. Sir, the first question we received from Amrita Sarkar. She says, "Good afternoon, sir. Where this vacuum tube or the thermal bulbs are used nowadays?"
Can you repeat the question? There's some disturbance in the audio.
Sir, am I audible to you, sir?
Yeah, 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 please.
The question, first question comes is, where this
I can, it's not audible. I think if I got the question, is he asking that what this vacuum tubes are used today? Is this the question?
Sir, I have put the question in the chat box.
sir, is it audible now?
Yeah, it's
So the
audible.
first question is,
So,
where these vacuum tubes or the thermonic bulbs are used nowadays? The question is from Amrita Sarkar.
yeah, yeah. Yeah, I already mentioned in my lecture that these devices are used where vacuum tubes are used where you require a high power, right? Because semiconductor devices have a limitation of this power dissipation capability because of the size, right? Small size. So whenever it comes to handling high level of power, it is vacuum tube. I have given an example that in broadcasting radio stations, right? Transmitters, they use the vacuum tubes because you have to produce large power, right, for broadcasting purposes. So this is one area, and microwave tubes are used. They are also when you want to generate microwave power, good amount. Again, it is even though you have a lot of sources which are semiconductor sources, but these tubes are very much in use in microwaves.
Thank you, sir. Okay, sir, the next question we have received from Adya Mile. The question is, where these Tilby strips are used nowadays?
Hello.
Yeah, sir. Hello.
Yes.
Yes, so the next question is from Mile Adya. She asks, where these Tilby strips are used
You are
nowadays?
not at all audible. At least I cannot hear. Please, I request all others to please mute so that I can hear because a
I,
lot of echo is.
I request everybody to kindly mute. Mute. Thank you. So the question is, where the Kilbis chips are used nowadays? This is the question we have received from Mile Adya. Hello. Hello.
Sir, you are muted, sir.
Muted because lot of disturbance was there. Now is it?
Yes, sir. Yes, sir. Yeah.
Which question can you show me that?
So the question is from Mile Adya. She asks, where these Kilbis chips are used nowadays? Sir, can you mute?
Kamalika, put the question in the chat box.
Ritual, what is
Okay,
vacuum
okay,
tubes or galvanic valves?
Kamalika, put the question in the chat box. I can see it from there.
okay, sir.
Are you asking the same question which I have answered where the vacuum tubes or galvanic valves are used nowadays? Is it the question?
So the question is, where the Kilbis chips are used nowadays?
Write it on the chat box. Let me see that. I cannot hear.
Okay,
Please
sir.
write the question.
Yes,
I see one question from Sudev Dasgupta that your views on two disruptive technologies in next decade in the domain of semiconductors. So that I think I have already answered this. One disruptive technology, probably I discussed about your CNT FET which is going to come, or graphene based transistors which are going to come, could be one. But I do not see much future of this uh, because 1998, if it is proposed that it has not progressed that way, and there are a lot of practical difficulties associated with that. So I don't think it will come. And if disruptive technology will something which will not be a small change in the existing technology, it will be altogether a new concept. So I think I see that quantum computation and even optical computation was in discussion for a long time, but also it didn't flourish the way as your superconductors people believed one time that superconductors will be replacing semiconductors, but that didn't happen this way. But Google and other companies are claiming that they have made quantum computers. So I see that that could be the a disruptive technology not only in the field of your the existing semiconductor industry, but everything. Or literally, it will change all this e-commerce and starting everything. You name everything. Information technology, it will change everything, and I consider as a disruptive technology. And uses nanotechnology is not going to cannot be considered as a your threat to your silicon microelectronics technology. And I don't see anything like that which can be really considered as a your disruptive technologies in the field of semiconductors. Semiconductor means I mean semiconductor manufacturing industries.
So we have one more question from Chanda Model. She is the faculty of our organization only. Her question is nowadays carbon nanotubes use water treatment. What is also used in water treatment purpose. So kindly discuss this point, sir.
No, not only carbon nanotubes, actually nanotechnology, the whole technology is used for multiple purposes. They have nanotechnology, you'll see that in general, lot of hype was created about the technology. And people really at one point believe that it will create changes in almost all fields, including the field of electronics engineering. But the nanotechnology has done lot of changes in certain areas. So in chemical industries, if you go, that whole technology of painting, etc., has tremendous things. The kind of finish you now get in your cars and other things. This is all because of this development in nanotechnology. The kinds of sensor you are developing today, they are nanotechnology is doing a huge difference even in drug delivery and different kinds of biosensors, chemical sensors, and other sensors. Your nanotechnology is playing a huge role, and in your water purification, your photocatalysis, lot of places is nanotechnology concept is used, and it has really made a huge impact. But unfortunately, in the field of electronics engineering, I don't see any threat on your microelectronics field, which is mature to this day, that this technology will have an impact and change the whole thing. I don't see. Right. But nanotechnology has a lot of other applications. There's no doubt about that, and it has already made a lot of changes in many places. But in this case, particularly, the way you see that in your this tiny device which you call mobile, you have everything there. Actually, you have a computer, right? Which is a portable kind of thing, and it's all because of your microelectronics technology. It is nothing. But you individually see the screen of your smartphone. Smartphone, there is a big role of nanotechnology, and even the new generation materials, which are organic materials, which are being used for smartphone screens today, which you call organic light emitting diodes. So in these certain areas, lot of nano electronic devices in the form of sensors are coming, emitters are coming, big size your panel display units. There you have the role of nanotechnology in a big. But particularly in this area, I don't see that nanotechnology will make a huge change.
Sir, today's last question because of shortage of time, we won't be able to take all the questions. The last question, sir, if you mention. This is a question from Ravindra Kumar Shah. Does the dielectric strength of materials play any difficulty?
Now, what do you mean by dielectric strength? Is not important. What is important is the dielectric constant of this material. If you use a high K dielectric, then your capacitance, you know that epsilon A by D, that capacitance part can be controlled and which needed for scaling purposes. So MOSFET devices, high K dielectric is used for that. It's not the mechanical strength of the dielectric, but the dielectric constant is important. Right.
Kamalika, there's
Sir?
one more question from Shwanjan Haldar. Please read it.
Okay. Yes, sir. Sir, this is a question from Suranjan Haldar. His question is, why we cannot convert electrical signal to Wi-Fi signal?
Into Wi-Fi signal.
Wi-Fi signal.
Why you can? Who said that you cannot do it? Electrical signal. That is the whole concept of your radio signals. What is radio signal? Radio signal is all about that. Radio wave. If you see the communication early days of telephony, was your basically you need to have a transmit path between the source and the transmitter and the receiver. In telegraphy, telephony, they used to be connected. But once this radio wave came, radio is basically your wireless. The whole concept of wireless is coming from there. Radio waves only. Why do you say that this is?
Okay, sir. Thank you, sir. Thanks a lot for your valuable talk, and we have a lot of participants who are constantly listening to you, and they are really enriched. They have particularly mentioned our thanks to you. Uh, now I'll request our HOD R&D cell, Professor Chandan Ghosh, to kindly give vote of thanks.
Good afternoon, everybody. Present virtually over here. Am I audible?
Yes, sir.
Yes, audible.
Yes, sir.
Honorable Speaker, Professor Dr. Parthasarathi Chakrabarti, our Honorable Director, Dr. Piyush Roy, our invited guests, students, fellow faculty, researchers, and other invitees. It's my pleasure to present virtually and to deliver a vote of thanks on this enriching occasion. I, Dr. Chandan Kumar Ghosh, on behalf of R&D cell of Dr. B.C. Rai Engineering College, extend a very hearty vote of thanks to our speaker, Dr. Chakrabarti, for sharing with us his opinion and ideas on the interesting topic journey from vacuum tube to carbon nanotechnology, nanotube basically. I also thank Professor Sorit Pal for taking initiative in organizing this webinar. Also thanks to faculty coordinator Dr. Kamalika Tewari for her active participation in this webinar. Thanks to Professor Das and Professor Banerjee for making right arrangement for the webinar. Thanks our distinguished guest, Professor B.N. Basu, ex-professor and head EC, IIT BHU, for his continuous support, suggestions and encouragement. Thanks Dr. S.N. Joshi, ex-chief scientist, CSIR, CEERI, Tilani, for his encouragement. Also thanks to great scientist Dr. Lolit Kumar and Dr. Vishal Keshari for their glorious presence. This webinar will help a lot of students and fellow faculties, researchers in future with respect to their career and research. Thanks to all concerned to be present virtually in this webinar, even during this pandemic scenario. Thanks the organizer and we look forward to organizing more webinars for the interest of the students, faculty members, researchers for their technical enrichment. Lastly, I would like to wish everybody good health and safety. Thank you all. Thanks again to Dr. Chakrabarti for giving us the valuable time for this webinar. Thank you very much. Thank you all.
Namaskar.
Thank you, sir. I'll request all the participants to kindly fill up the feedback form. Thank you, sir. Thank you, everybody. Thank you, sir, for joining us.
Thank you. Bye. Bye.